In this lecture, let's talk about how to find the maximum and the minimum values of a two-variable function. The concept is similar when we have a single variable function. When we have a single variable function, its maximum value or the minimum value occurs at the critical point, which is when its first derivative equals to 0, and we interpret that as when the tangent line is a horizontal line. Similarly, when we have two variables, on the right it shows a graph, and we can see that it has several maximum and minimum. We have the absolute minimum here, the absolute maximum here, and a local maximum and a local minimum. At these four critical points, their tangent planes will just be a horizontal plane, so similar to a single variable function. At the critical point, the tangent line is a horizontal line. And how do we find the critical point of a two-variable function? That is also similar to when we have a single variable function. So we take the first partial derivatives of the function and we set them equal to 0. And both values have to be 0 in order to consider the point as a critical point. Another way to view this is, at the critical points, their gradient of the function would be a vertical vector. For example, at this point, the gradient of the function will point directly downward. And at this point, the gradient of the function will point directly upward. So their gradient of the function at the critical point has no x and y components. That is also why we set the first and the second components of the gradient of the function to be 0. After we find the critical points of a two-variable function, then we can use the second derivative test to test whether the critical point is a maximum or a minimum. The second derivative test is similar to the second derivative test when we have a single variable function. But instead of looking at the second derivative, now we need to evaluate this whole equation, which is the second partial derivative with respect to x at the point, times the second partial derivative both with respect to y at the point, minus the second derivative of the function. It could be either f sub xy or f sub yx, and this value squared. And we've covered a theorem before. The order of the derivatives is interchangeable if the function is continuous and differentiable at the point, which is true for most of the case. Then after finding this value, the d, now we can perform the second derivative test. If this value d is positive, then it could be either a local mean or a local max. To find whether it's a local mean or max, we also need to find the second derivative of the function, both with respect to x. If f sub xx at this point is positive, then that means this critical point is a local minimum. So that is similar to a single variable function. When we have the second derivative is positive, that means the function is concave up at this point. And when we have a concave up, that means the critical point is a minimum. And the second case is when the second derivative of the function is negative. Then in a single variable function, that means the function is concave down at that point. So the critical point would be a local maximum. And the third case is when the value d is negative. Then that means the function at this point is not a local maximum nor a minimum. And we call this type of point a saddle point. Before we look at the example, let's make a few notes. In the three cases we covered, we only cover when d is positive or if d is negative. That is because if d equals to 0, then it is inconclusive. We have to use some other methods to find whether the point is a max or minimum. And the second note, an easier way to remember how to evaluate the d is using a 2x2 determinant. So d also equals to the determinant of a 2x2 matrix with entries f sub xx, f sub xy, f sub yx, and f sub yy, which equals the product of the first and the fourth entries, f sub xx times f sub yy, then minus the product of the second and the third entries. And for most of the functions, f sub xy equals to f sub yx, as long as function is continuous and differentiable. So we can rewrite that as f sub xy and squared. We'll look at a numerical example in this lecture. Then in the next lecture, we'll look at 2 more applications of this concept. So let's start with a numerical example. Find the local maximum and the minimum values and the saddle points of the function x to the power of 4 plus y to the power of 4 minus 4 times xy plus 1. To find the max, min, and the saddle points, we need to first find the critical points. That is when the first derivative of the function equal to 0. And we have f sub x and f sub y. Both functions have to equal to 0 in order to consider the point as a critical point. For f sub x, we get 4 times x cubed minus 4y. And f sub y, we get 4 times y cubed minus 4 times x. And both equal to 0. Now we have 2 equations with 2 unknowns. So we can solve for the x and y, and that would be the critical points. From the first equation, I can rewrite that as x cubed minus y equals to 0. Then I isolate for the y, I get y equals to x cubed. And let's call this equation 1. Then from the second equation, I can do the same thing. So I divide it by 4, and I get y cubed minus x equals to 0. And let's call this equation equation 2. Then I can substitute equation 1, which is the y, into equation 2, which equals x cubed to the power of 3 minus x equals to 0, which equals to x to the power of 9 minus x. I can isolate for the x, so x times x to the power of 8 minus 1. Here I have a difference of squares, so I can rewrite that as x to the power of 4 plus 1 and times x to the power of 4 minus 1. The x to the power of 4 minus 1 is again a difference of squares. So I can expand that as x times x to the power of 4 plus 1, then x squared plus 1 times x squared minus 1. And x squared minus 1 is again difference of squares. So I rewrite that as x plus 1 times x minus 1. And this equals to 0. Then I isolate for the x. For the first term, x could be 0. For the second and the third terms, they will always be positive, so they cannot be 0. And for the last 2 terms, x could be negative 1 or positive 1. Then I substitute them back to equation 1, and I get 3 critical points. First one, when x equals to 0. Back to equation 1, y will also be 0, so first critical point is at 0, 0. The second point, when x equals to negative 1, if I substitute x equals to negative 1 back to equation 1, y equals to negative 1. So the second critical point is at negative 1 and negative 1. And the third critical point, I substitute x equals to 1 into equation 1, y will also equal to 1. So the third critical point is at 1, 1. Then to find whether the critical points are maximum, minimum, or saddle points, we need to evaluate their value d. And we'll need the second derivative of the function f sub x, which equals to 12 times x squared, and f sub y, which equals to 12 times y squared. And we'll also need f sub xy, which equals to negative 4. So the value d would be a function of x and y. That would be f sub xx times f sub yy. That is 144 times x squared times y squared. Then minus f sub xy squared. That is minus 16. Then we substitute the 3 critical points into this function. The first point at 0, 0. The d would be negative 16, which is negative, which means this critical point represents a saddle point. And the second critical point is at -1 and -1. So I substitute -1 and -1 into D, and I get 128, which is positive. Then I'll also need to find the sign of f sub xx. F sub xx at this point, -1 and -1, would be positive 12. Then using the second derivative test, this critical point would be a local minimum. And to find the value of the local minimum, I substitute -1 and -1 back to the original function. And we get the function is -1. So this point is a local minimum. And the last critical point, at 1, 1. I substitute into function D, and I get the value is 128, which is again positive, so this point will either be a local mean or a local max. And I need to verify with the second derivative of the function. So f sub xx at 1, 1, that also equals to positive 12. That means the function at this point is also a local minimum. And to find the value, I substitute the critical point back to the original function. And I also get -1. On the right, it shows the surface of this function. So we found that at the point 0, 0, the function has a saddle point. And that is how the saddle point looks like. So the saddle point looks like a local minimum along a plane, for example, on the xz plane. However, the function looks like a local maximum along the yz plane. So a saddle point is when we have one side that is concave up, but on the other direction, it looks like a concave down. And we also found that the function has two other critical points, one at 1, 1, and the other at -1 and -1. We found that those two critical points are both a local minimum, and the value of the function is -1. And that is the end of the lecture. In the next lecture, we are going to look at 2 more examples on this concept, and there will be applications of this concept.